So it's running. So during the last lecture last year, we have started implementing an own IPC mechanism using Windows's ALPC ports. So it's a Windows proprietary solution, but it has various advantages over using pipes or network sockets. Also some disadvantages, but depending on what your goal is, it might be a good option. So we wanted to implement it, and we wanted to do it such that we more or less emulate how Qt implemented that pipe communication, so that if we have an application that was using Qt's local server and local sockets, it could be very easily replaced with our own ARPC port-based implementation. And we started with the server, and we progressed as far as we did with a lot of to-dos, and then the lecture was over. So now we will continue. But since um, I think we already put enough work into the server at least to get a connection inbound, we can quickly run it to see if we see an open port. We will this time start with the client side, see how far we go, and then if we manage to finish the client side today, then we will just debug the server and finish whatever is missing. Let's see. Okay, we need to add this functionality to our test panel, as we might remember from when we started the whole thing. We have created it such that we have only one binary that does all the different tasks, and we can start different versions of it using the buttons that we have here. So let's quickly add two more. And this is the not local server, but let's call it port server. Port server Qt and port client Qt. Okay. Let's grab one of the button names. Okay. Okay, let's do it manually. Port local. Oops. Port server. Port server. Port server and name my port. Start process. Okay, then domain, and then we copy those two and adapt them accordingly as well. Ports. Okay, port server and port client. Okay, and when we start the we should have also renamed the buttons. Let's quickly fix that small oversight. On port server find. And this, I just only change the names to pipe, so that it's clear what is using what. Okay. And run. Okay, this thing is running. Let's see, we have here another instance. Handles, ALPC ports. Not seem to have opened the port. Then we forgot to do something. Let's quickly debug it. So we go to our server here. So port server. Okay, we open listeners here. So let's put a breakpoint here. Let's try again. Okay. My port. Zack. Returns false. We could have created a port successfully. Let's try again. It might be this port. It does not tell us the name. Let's see the handle. 3cc. Okay, so this is for some reason our tool here is just unable to show us the name of the port right now. That is not great, but it means it will be working. It will work when we try to connect. We just don't see the port name here. So this should be fine. So let's start implementing the client section. So we have started here implementing socket and this thing. As we see, it's not yet quite complete. A lot of is missing. Basically everything is missing. So we have enough things to do. We will start with similar approach that we create such a private structure as we do here, since it's quite useful for us to have a lot of things abstracted, hidden away from the rest of the framework. Private struct *m ptr, just the same way as we did here. Okay, and we'll need, let's see, well, constructor and destructor, obviously. A critical section might also be useful, so let's add those thingies. We can of course grab all the includes. They are probably quite useful as well. Then we of course need our critical section. Although maybe we will not need it. That will be seen depending how we want this to be implemented. We don't have anything here. For now, let's comment it out. But if we decide we need it, it's here. And we have a handle. It doesn't need to be volatile client port. Okay. So these are the basic things that we require. Buffering and things like that will be done by our QIO object, so we will not need anything individual here. We might need some helpers. What also will be certainly useful is to cache the port name. So we should add some name variable to our internal thing as well. Having the name remembered is always good. We have here connect to server with name. So here, first of all, we of course need to instantiate m. And equals new thing and delete it once we're done with it. And here connect to server, we can start with client port. So if this is, then it is already connected, and we just return because there is nothing to be done. And else we start with setting the name into a standard string. We will need to open our own device. Oops, not that. We will also need to do open mode. Close is something for later. Okay. It's of course a bit unfortunate that this the original doesn't have any return value. So if we try to connect to something, we are already connected. We either should first disconnect and then reconnect, or we will silently fail this. So maybe we change this here. That if it is connected, then we disconnect and then we continue connecting from scratch. I think this is a reasonable approach. This thing will definitely close the device. Whether we open it now or later is to be seen. Since we might only want to actually trigger open if this was successful, we also need to remember that we will need to emit connected and disconnected signals. So emit disconnected, emit connected, but there is more to do here. Most important, and if this is nothing, then we just really do nothing. If this doesn't exist, then return, because then it was already not connected, so there's nothing to be done. Yeah, good. So we have our port name. Now let's connect to it. So first we need again a few Windows specific thingies. Security, security quality of service. Length is size of this thingy. Quality of service punct, impersonation level. So the way these ALPC ports on Windows are used is generally to implement remote procedure calls, so that you call a function but not in your own process but in a different process, and this other process then does something and the results of this operation are returned to your application. And for this, given that usually those ALPC servers are running as system, you wouldn't want most of those operations that you might want to do to be executed as system, because system has all the privileges, at least most of the privileges, and can do a great lot of things. And if you have just a normal and limited user, then you might not want them to be able to call functions with system authority. So the way this ALPC mechanism works is that when a call comes in, then the server can impersonate the user which is executing this call, so that for all the security checks that are then performed in the context of the thread which is executing this ALPC call, the security check functions will all see the token of the user and not the system token. And here, when connecting to such a port, one can specify which level of impersonations should the server assume. So this doesn't change that the server will always impersonate the user, but when doing so, there are different levels of how many user privileges the server might then be able to use. This is quite useful when, for example, wanting to limit it so that it cannot authenticate against other servers online, or other limitations. There are not many levels. We have basically 3 of them plus anonymous. Anonymous basically means that don't impersonate the user, but at the same time it will then impersonate an anonymous user, so that the server will have no privileges at all. And then we have like a security identification, that is, it can identify the user, but it cannot use the user's privileges. And impersonation and delegation are two levels of how much of what the user is allowed to do the server then would also be allowed to do under the user's token. Then we have a few more parameters. Context tracking mode. Test we will set to security dynamic tracking. There are also not that many. There is just dynamic tracking and static tracking. And as you see here, just evaluates to true or false. So this is just a on-off switch. And last one is effective on set to true. Okay, then we need the name of our port. Unicode as Unicode string port name. RTL initial needs a Unicode string. Zack, reference port name, comma m name punct c string. So this function, as we might remember from the last lecture, will initialize a Unicode string structure from an existing string. So this string is not allowed to change as long as we are using port name, and it will not change. And also this is why it's helpful to cache this as a string, because this uses the same character type. So if you would have just a normal string or use a different character type, then it would not be compatible with Unicode string. But since we use the right type, it is compatible, which is a bit, it's quite convenient because we don't need to create a copy of the string, etc., etc. So it really initializes this structure just with counters and references to data stored inside our stdw string. Okay, so let's open the port and status enter connect port. And this is also missing. As we might remember from our last lecture, a lot of the things that we have that we wanted to do use APIs which are not publicly well, they are publicly known, but they are not exported by the standard Windows SDK. They are defined in the NTDLL, etc., etc. But we need to bring our own definitions so that we can use them. And people have reverse engineered those definitions. So this is by now quite reasonably documented. It's not perfectly documented, but it's good enough that such things can be easily used when necessary. Find scores null we should this will be a returning value. This will give us what the port supports. So let's add here another variable. Long max data len. Start with 0, and when we connect, we will read that back. So reference connection information, that can be null, and connection information length also null. Oops. Okay, and then we check if it was successful. If enter success, status, or rather if not enter success, then we'll just bug out. Don't we have this defined? Use that. Where is this defined again? I think that is missing. We could just define our own. Let's do it here in those devs. Basically, we just check whether the thing is greater than 0, and if it is, wait, I had a typo that maybe it is defined. Yeah, it was defined. Basically, it just checks whether the thing is greater than 0, and if it is greater than 0, then the operation counts as successful. execute. And so if it failed, then we basically just bug out because something was wrong. We could emit some error. Do we have a signal for that? Well, error occurred. We could emit something, but this would be then specific. So let's just add here a to do. Error, emit error occurred. We also need a few more things here. Another variable, size of port MSK, size of port message. This will be the header size, so that we know how much data we will always use for the header. Caesar of port message. Okay. And if we successfully connect it, we will subtract this thing here from this thing here. Size of port message minus m. I mean, we don't really need to make this, to change it, because it's always the same value. We could also put it globally here. That will be const size of port message. Then if we have multiple clients, we save a bit memory. Yeah, that is, I would know this of course is nicer. So effectively max data length will then contain the amount of payload we can send through and not the raw package size, which is what we are mostly interested in. Let's change it. There is a reason why this might need to be dynamic. That is that depending on what we are doing, so if we are on a 64-bit system or if we are on a 32-bit system, this will change. So if I will not implement it because we will need to use a function which I'm not sure we have defined here, but then basically this thing would be plus would be bigger by so much. And the idea is that a 32-bit application, if you would compile a 32-bit application, would dynamically with a function that tells it whether it is running under Windows on Windows or if it's just running on a real 32-bit Windows. It would tell us this, and then we could here select the right size. But usually nowadays we only do everything in 64-bit, so I'll leave this here so that this is visible that such a workaround might be necessary, but we will not spend our time into actually implementing this. Although we might, let's see, if what was the name? Is Wo64 process. That probably is this. Get current process. Yeah, okay, and comma reference. The downside, of course, is that now the code will not run on a, let's say, on Windows XP, because this function is only exported starting with Windows Vista, and it returns true actually on if it succeeded, like to check, and the result of the check is returned in a variable. So if both are true, the check was successful and this thing says it's true, then we just do this. But as said, this we really only need on a 32-bit system. So if ndef v64, or was it like this? There is some macro, yeah. So this code will only work if we would switch this to, which we cannot even do unless we add a new configuration, but just as a demonstration how such things would operate on a 32-bit system. Right, so we have our connection. Yeah, and if we have the connection, then we are connected. Then we don't need to do much more. We just open and emit connected. So let's try. We put a breakpoint here. We run it. What did we scrub with the connect port? That needs another header, I think. Not header, another include. I guess this one. We will see whether that was all we need or if we are missing something else. Nope. I mean, in principle, I would expect this to be in NTDLL, but for some reason it does not. No, I know what we did wrong. We have here this extend C, and this, of course, the new code must also be within that. So I think we can remove the library again. It should really be in NTDLL. Yeah. Okay, so run server. With our server. Now run client. And we did not connect. We didn't even try to connect. So something is not quite right. Let's go to our main function. Add a breakpoint here, or just look into the constructor. But we have a connect to server, so we should try. Creating server works correct. Creating Qt port client, that should looks fine. Connect to server. Oh, we still are using the wrong port. We need to switch this to our own how do you call it? Port server, port client Qt. Port client Qt, IPC port, port socket. Port socket. This needs to be changed, and we need to include that hash. Port server. Let's quickly see in our server here. That was the path where we have those thingies. Port socket. Okay. It's not quite happy. Okay, what have we broken here? Okay, this thing here is wrong. This also needs to be of this type. Just look wherever we have now got some. Oops. Okay, this was apparently everything. Okay, so port server, it's listening. Port client. Now I should start to connect. Yeah, we are connecting, so we go through the disconnect just to be safe, but of course there is nothing. Then we get the name, my port. Then we prepare our quality of service structure, and then we try to connect, and we see it failed. Okay, not great. That of course might be related to our port here not properly displaying its name, so we might have not set up everything, but at least we have the client side that we could test. Right, we could have checked what the error message actually means. Let's quickly do that. Breakpoint goes here, so we get this value. Just type some tab we can go to the file where we are from. Object path syntax bad. Okay. I know what's the problem. Unlike with pipes, we need to provide a full path for the port name. What was that? Will be different. Okay, so we have the same problem in our server. That's why we didn't see the name. Listen. Oops. Name. Oh, and we have another problem. We have forgotten to set the name. That's of course also great, or rather not not great. String v. Okay, and now let's fix the names correctly. So we need this is v string, so L RPC control. I think this is typo free. And then the name, like my port. This the same fix we will need to add to our client. Okay, let's see. Start the server. Don't need this breakpoint. Let's now see if we see the name correctly. Yes, we see the name correctly now. So this should now also connect. Connect client status 00 is success. And when we look here, we already see that it was connected. We have one waiting for connections and one connected to our other instance. So this works nice. Now next thing to do will be to complete our server. So we have here a thread function which processes things that happen. So let's put a breakpoint here and observe how this behaves once we connect. So we get here a connection established message, a connection request, then we go on port connect, which we already have implemented. Nice. This we don't care about. Okay, and then we are basically waiting for something to happen. So now our client should send something and wait for a reply. Unlike the pipe and socket based communication mechanisms which we have used in the past, which are quite bidirectional, so basically every side just starts sending bytes and the other side receives them. The um, port mechanism is more transactional, so you are sending a request and then you are waiting to receive a reply. You are not you don't have a direct mechanism to just be invoked from the server again, since this is not something that you would need for remote procedure calls. The downside here is, of course, that if you would have some status in your server which you would want to be notified about changing, that will not work. You will need either a auxiliary mechanism to do it. There are some complicated ways how this can be done using this RPC mechanisms. Basically, you would create a event object and then give a handle to that event to the server, and the server then would be able to trigger that event. But this is kind of outside of the scope of how Qt handles things. So implementing such a mechanism would be not well representable within how you expect things to work when using a normal Qt local server. Of course, a very custom implementation could be done that then emits events, etc. So we might take a look on this later. But for now, we will want to make it as simple as possible. Basically, we just send a request, wait for a reply, and when we get the reply, we trigger the data ready read event so that something then is read back, and thus we get a mostly drop-in replacement. Okay, so let's go back to our socket. So our socket has here read data and write data, which we have not implemented. So I guess if we put a breakpoint here and run it again, we will see that we arrive here with some test message. Since we send on successful connection here on connected, we are sending a hello string. So this comes in here. We have our hello, we have its length, but what we don't get, of course, is any reply because we just say we bugged out with an error. So that now we need to implement this mechanism so that it will work correctly. And this we will do by adding either a transactional function that we then send a buffer the data and put the event out of here, or I think this is the easiest way, so let's do it like this. So we will need some buffer that we will get the result into that we can then present in the ready read event. So the buffer we could implement here, since it will be just a Qt sort of byte array. Receive buffer. In principle, we could make it like a list of buffers so that we maintain the message nature, but since the normal pipe server doesn't do that, then we will here also just bunch the replies together if they would happen to arrive multiples. But ideally, normally in this situation, we would read something completely before we issue the next operation. Also, we can improve this behavior later on if we want. So socket. Let's start with our write mechanism. We will probably also need we might need a send buffer, although I think we don't need to keep it persistent all the time because we just get some data. Well, that is of course another limitation, since the other side expects to receive a whole package. Here, when we write something more like streamwise, that those packages might be broken up. This is, for example, one of the reasons why on the UDP network sockets, the mechanism bypassed the normal read and write functions and had read datagram and write datagram, because on UDP you also need to maintain the whole thing be working properly and not breaking things breaking things up or bunching them together. For our application, we want this, as I mentioned, to be a drop-in replacement, so we will just rely on write data to be always triggered with the whole package size, and we will just send this as one thing. So it will be basically an instruction for the user that they should not like write multiple. Though this is also not elegant, because if they write multiple things, so if you want to use this as a drop-in replacement, you might feed this object to some other class which expects that it can write to it like to a pipe. So basically what we should do is we should cache everything and then require a dedicated flush buffer instruction to really send the data out. This is of course not ideal. Mostly because then of course we also really need to change our implementation of this thingy. So how we operate it, client here, we have this send data, and send data is appends to buffer, and then we have our buffer, and this thing, once we have our buffer full, tries to write everything from our buffer. Let's see. We could implement it such that we can kind of handle incomplete sends, in which case we would maintain an own packet structure and feed results. Okay, I think this will be a necessary design choice if we want to maintain this somewhat stream-like behavior. This will be required. Yeah. This is not pretty, but let's go with it. So on this end, we will do it like this. We will really send everything out, but the other side will accumulate data, and then it will only answer to those parts of the accumulated information that could have been already processed and replied. So you will either get an empty reply like not enough data, or you will get a reply which might contain multiple replies in one. This is, I think, the most elegant solution we can implement here, really. So let's see. So we have our write data. First of all, we need to check if the port is working. So if the port is not connected, then we return -1, indicating that the port wasn't ready and something failed. We will not add any auto connect mechanism. We'll now need a somewhat large buffer, not that large, to send and receive data. So future request buffer. Did we define the max port length? I think we did. No, we didn't. We did, but here, so let's move this to our defines so that we can use this on both ends. Okay, so we have here our buffer length, then port message, request header, port message, request buffer, ultra request data is request buffer plus m size of port message, so that we skip the header. Then the same for the reply. Response buffer. That's also port message. Response header. Port message. response buffer, response data, response buffer plus port message. Okay, then we don't need anything else buffer wise. Then we have here our incoming data to be sent, and if we receive something, we'll feed it into our receive buffer that is waiting. Okay, so while length is greater 0, so as long as there is something to be sent, ulong send len len is greater than m max data len, then max data len. So we cannot send too large messages either. So there's also a limitation with the basically with a pipe mechanism or a socket. We can just start sending a 4 or 10 gigabyte large file and then just send and send and send. There is no limit. But with UDP, you might remember there is a limit, usually about a kilobyte. So here it is kind of similar. We have a package limit, and if we want to send larger things, we need to make an own mechanism around it that will break those things apart and put them back together. So here we are doing this breaking apart. If it's too big, then we just send a small portion, and then we just repeat this in the loop until everything has been sent that we wanted to send. Okay, so set. First we set the header. Set request header, comma 0, comma size of port message. So we reset it so that it's cleaned. Since we are reusing the same buffer in this loop many times, it might things might change. So request header, union 1, struct 1, data length is equals send length. This is of type ushort, so let's convert this correctly. Then one punct total length is equals basically just the same thing, just plus this thingy. So it's a bit redundant, but the mechanism requires both information, so we need to provide them. Now set request data mcpe request data comma buffer. We will need a few helper variables. I will modify those. Let's just get those. So let's get this as is, comma, and size is sendlen. So we set our data. What we might want to do data yeah, and yeah, let's continue. So since we have copied the data, we can advance our data pointer, and then minus equals this, and then we can send the request. So enter status is equals enter request. Wait, and this is also not implement, not define. So let's add this here. Socket, enter, wait, reply point. Yeah. Now we pass the handle. Client handle, comma, port, message, asterisk, recu buffer. Actually, we could just use the header since we are not advancing it anywhere. Directly should be fine. And port message reply. Response header. Zack. Okay, so if not enter success status, so if something went wrong, then to do. Basically, we just break connection, emit an error, and are done with. And else, well, no else. We could return at this point if it breaks. Just return. And we need one more thing. We need a temporary variable which keeps track of how much we have sent. Send total 0. So after it was successful, send total plus equals send length. And of course, once we are done, we return the total send length as a return parameter. Okay, so we have checked this. Okay, so if buffer length, so if we still have some data to send, and response header u1.s1.data length. So this happens when we already get some reply, but still have things to send. So in this case, we would need to handle the early reply, which might happen if that bunch data together and we are sending them from some buffered situation, that we get here a reply. Right, buffer len. So basically we don't care for buffer len. We just are here, and if we got a reply, we will process it. And once we're done processing, we'll resume sending whatever else might there be in our buffer to be sent. Okay. So we need to check whether this is large enough. I'm thinking whether we should create like a helper function, but I think we will just implement it in here, and that's it. So we check if this is actually valid. So if reply length is greater or equals size of SQL message header, the right message header, port message, define message header somewhere. We should have defined that. We need our own message format. Um, yes. Okay, so we will need some own message format because we said that we'll be breaking the things up into smaller chunks. So we will need to define this somewhere that will be common to both of our server and client. So let's create a file for that. Networking IP QT new. Wait, we don't have a text file. We'll just reuse one of those files. Port defines port defines. So here we define things which are not part of the well, are not just part of Windows, but we define here things which will be special to our particular implementation. So type def struct port message header. We also call it like my port message header or something. Message header. Let's just message header. We want a size. Some flags. Maybe. Maybe not. Let's just go with long size. Now in principle we could also go with something and it's not defined, so let's use in principle we could also go with a 64-bit integer, but usually when you are doing some IPC communication, probably will not be sending messages larger than 4 gigabytes. So I think using an integer here for our own messages should be good enough. Now let me think. We might need this, but I think we can for now maybe do it without it, because as we said, we want to emulate the stream communication, in which case we would not need to validate actually that the size of the header is fine. We would just feed it into our buffer, and then the layer once higher would need to handle this packaging and sizes. Okay, so let's simplify this. Yeah, let's just feed it into our buffer. So our buffer, this will then be plus equals qbyte array response data, comma length, port socket. Why is this complaining? It should not be complaining. We should have Yes, I have a typo. We used this already in many places. That should be fine. I had the typo. I switched byte and byte. Here it just doesn't like the uchar. It just wants a char. Right. So we got the data from this thingy. The buffer, we don't need to advance it because we're always adding to the back. So what we need to do now is to check if we can receive more data from the server. Data buffer, advanced buffer. Data links. Request link, font size, message. We will look how we proceed from here. For now, let's just do this and write a to-do here for later. We'll need to check how this behaves when we have more data running in our queue. Right, so we have our request. At some point, we get a reply which contains some data. And buffer length. Yeah, that might be a bit not great because this thingy it also waits, and we might don't want to wait. We could implement it such that we are sending like an empty request, and then each time we are receiving something, and when there is nothing more to receive, we will receive an empty reply. That would be one way of doing it. So we would clear, let's quickly implement this. So we would clear the header for our next request, and this is then already null and null. This needs to be so this will be 0, and this will be just size of port message, so basically an empty request. Since this is 0, we don't need to let's keep it. Don't set any data because we don't set anything. We send a request again. Then we need to check whether it was successful. Thinking how we can make this more elegant. We can we set send len to 0 here, and then basically want to repeat the operation from here. That might complain that this is then defined here, so let's just move this here. So what we do, we prepare an empty header, set empty header. We set length to 0 since we already incremented this thingy here, and then we just go to receive next, which basically brings us here, and then we repeat this, and then we do this basically as long as we get data. And once we don't get, or rather once we get a reply with an empty data block, then it means the other side doesn't have any more data for us, and which is when we resume from the top, sending the next block, and then again we would run into this loop, which is of course not the most elegant. Let's maybe make this the real loop, since gotos while working are quite frowned upon. Do while well, let's go with for loop. Let's go with a simple for loop. Right, so we do this. If we have a bug, we bug out. If this was successful, we set it to 0 and then set this to null. Then we check if there is, so if this is null, then we are done. So if this, then break, else we receive the data, null the header, empty header, and then we receive more from the top. That is elegant. Can we make it even more elegant? No, I do not think so. Yeah. Good. So let's proceed. So we have this. This in principle finishes our whole thing. We always bug out if something happens and we get an error message here. So let's put a breakpoint here. And then to our server. So reply message. And the breakpoint here, and let's run it and see how far our implementation goes. What's still missing? So server, client, we get here a connection established. Then we end up here, so we send a request. So now we are then in the server. Then we have a LP request, nice. So we look up whether we can find the client. And we did not find the client. This is not great. The idea was, did we not implement? Yeah, we have not implemented that function. So now we know what we are missing. Let's see what we have in our port message. Alright, so we have the process ID and the thread ID. So this is all we need to know to dispatch that properly. So let's go to our function here. We have this clients. So we'll need to lock our critical section. Obviously, we'll need to unlock it once we are done. We need to cache the return value. Peg null ptr. Oops. Return whatever we have found in the meantime. In principle this is fine, but here we now are on clients. It should really not be complaining, it's just complaining because we are where we are. Oops. And now of course we check if this is not null. We go just with the thread ID. We could add here some more validation like check pros ID, etc. But since we here want this to be a quick implementation, we don't. F. No, let's be like this. Second punct. I think second is already our client. How did we define clients? Yeah, second is a pointer to the and we here, if you're using smart pointers, then we of course should stick to be using smart pointers. So we copy the thing here and then we return it, and then if we go there, then we just go with a smart pointer, though everything else is then complaining. So let's quickly fix this here as well. And there. Okay, I think now it's happy. Right, so this breakpoint can go away. We put a breakpoint here or here. That will tell us whether we get the client. We should get it, so this will be just for checking. Port, run. Okay, step, and we found our client. Well, it has our data. It doesn't have any other things yet set. So we are checking if we are already replying. So we should not be receiving another request while we are replying. Port request, I think, is also not implemented. So the next thing, of course, will be to implement port request. So we go there and we have already our client and we have the port message, so we can get the data. And let's see, so port server. Well, we did not implement this yet. We are missing a few things. Because we should have, when we ran into this situation, now also created a new client for this part of the mechanism. And in principle, so what is being used by the Qt local server is just the same socket object as it is used by for communicating. So we always have local socket. In our case, port socket here is a bit different, but we can, I think, reuse it. We will be just implementing like two versions of the thing. Okay, so we have our port socket, and then we make a port socket. I mean, we can either just derive it and then have two different ones. Yeah, I think this would be the way to go. Or we just implement everything inside the thing and then have a flag that differentiates whether we are communicating through a server or not. Let me think for a second what would be more elegant. Yeah, let's not create a new object. That would complicate things. But we'll probably need to have a send buffer later on in here. So this thing, in addition to those thingies here, although what we could also do is we could have two different private objects. But for now, let's also not do that. Let's just put everything here. What we'll need will be a reference to the server that we have been created from, although not necessarily. No, not necessarily. So normally the way is like this, that even if you have your client socket, you can write to the socket at any point in time, and if you're using a pipe or a normal network socket, then the data would then be sent to the client. Since we here don't have the means to actively push something to a client, when we write something to a socket on the server, we will always just write into a buffer on the socket object and this data will be kept there until the server comes, until the other client comes to the server and says, hey, I have here something, and then they will start communicating until both of them run their buffers empty. So here we will not need such a thing. We will need, of course, some flag indicating that we are a server-side socket, which means that every write operation will just go into a buffer. So let's create a buffer here. Send the buffer, and so connect to server needs this. Disconnect from server needs this. So let's create boolean or is server side socket false? Just is server side or is server socket? Let's give the full name. Is server side socket. This is by default false. Of course, if this thing, if we try connect to server on the server side socket, then this is not valid. So if m is server side socket, then just return and to do emit error. We had like an error, something somewhere. Error occurred. And here we just set emit error occurred. That will be for later. Disconnect from server. We kinda cannot really do this server side either. The client has to disconnect on their end. So here the same thing. If this is the case, then we bug out. Then of course here if so this will split into two. Protected write data server. But these are not virtual, these are just ours. Oops. Reading data will be probably the same. As you see, I have not planned this out up front because I was thinking that if you always plan everything up front and then you're just implementing, then people think that that's how development process looks. But if this lecture is supposed to also work for people that are beginning, then I think showing the full development process, including that you are sometimes running into a dead end and then to have to go back and then rethink your strategy, is something that will be pedagogically valuable, and also mostly by making people not develop too many complexes if they cannot do all the complicated things instantly, like one might think people do if one just only looks prepared, scripted and cut content. Right, this goes away. So we have here, and this is of course wrong, that should be switched. Okay, then let's change the order in the header here as well. So we have two functions. They both will do the same conceptually, but they will differ on which end they are implemented. So we have here just our write data, and if m is server side socket, then return write data server with those data. And else we are not connected, we just bug out whatever, and else. Or actually we could do it like this. This is more elegant. Write data client So if we are a server-side socket, we use the server function. If we are connected to a client, then we use the client-side function. And if neither is true, then we just bug out because we cannot do anything. This is basically equivalent, since the other returns will not allow the code to pass, and this kind of just looks better. So let's format it like this. And so here the server-side sending will be very simple. We just add stuff to the send buffer, as we did here with the receive buffer, just that we feed now here our data and length to it. Okay. It's complaining. Should not be complaining. Yeah, it's fine. Just some IntelliSense not being consistent with itself. Okay, so where were we? Port server. Right, we have our port reply. But I said the first thing that needs to happen is when we go to our port server here on connect, this needs to be triggered. We need to have a pending connection. We need to trigger the new connection slot. So this data is fine. This here we just put breakpoints for now. And here we have our port connected, but this is in the thing, so it cannot emit anything. So from here, when we have the connection established, we are in a worker thread. This is also not great. We have just our M's. Terrific. This M thingy needs to have a reference on ourselves so that we can emit events. So this port server. You can either give it a proper name or just use one letter. I think Qt uses. I don't recall. They are using some shortcut for always the parent object. I just call it Q. Point on Q or this. This is nice. We could use this, the capital this. This is nice. Yeah, let's do it. Let's call it this, and then we need to call this, well, just object, and we define this as a friend. For later, friends talk private, so that we can call private things on this thingy. Okay, so then we are here on port connected. We leave the critical section and we can emit. This. What was the name of the thingy? Local new connection. Emit new connection. And then so the next thing is that we need to implement the function next connection. What was it? This one. We can test whether it works. We basically expect to get into this and then return null, which is kind of inappropriate. Something must return a value. Right, this here must return len. Here we always say we succeeded, unless the buffer is too large. So to do add a buffer limit. Maybe. Let's run. So we make a server, we connect. We already run here into our event, and then here we have on connection. So the order of things is a bit random, but this is normal. I mean, it's not really random. It's just that the client side makes its connection, and then it's already ready to send data. So it already starts sending data, and depending how the CPU scheduler on Windows schedules the different tasks, it then will happen in the one order or the other. And now on the other end, we have here our next. So this thing needs to create a Qt port socket of marked as a one that comes from the server. But so the way this normally works is you have a list, and then you just train the list when this function is called. Since we already have kind of a tree or a table, what did we create here? Clients is a unsorted map is a table. So we either add another list like pending clients, or we just always go through the whole table and have just a flag which indicates whether the client was already given out or not. Both approaches are okay, but I think the list will be the more elegant approach, since it will ensure that we don't waste memory. So if we would have a flag on every client, then this memory would be always used, so that would not be great. And if we would have like 100 clients or so, then adding every new client might mean traversing the whole 100 clients and checking, so that would be wasteful CPU-wise as well. So such a list adds maybe a bit more complexity to the code itself, but ensures that we are, in terms of memory and of CPU usage, more efficient. So we just make a std list. And we have here this pointer, and we want a second pointer type, weak pointer ref. So the idea is that if we use a weak pointer in our list, if this client would go away before the next client function is called, then when we drain the list, then we would just get a null pointer effectively, and then we just return null. Or what we can also do is then we just skip to the next client. Both approaches currently are equally valid, depending on how we define the semantics of our new client slot. That might not be the case, so we might define it like that if we are in the slot, we can call a function get next client's ID or something, and then we would need to keep this somehow synchronized. But since here we will just say if this is triggered, get the client and then check where the client is, then using this approach with the weak pointer is the more elegant way. So list ref new clients small l new clients. We keep locked, so here before we emit, we add two new clients punct push back our client, and then we unlock, and then we go on a new. So now we need here something that will give us a new client. So it's what was the name of it? Client ptr get new or get next client get next client capital G. So here we lock our, basically we just do it like this, zack, unlock. Basically it's like with the find client somehow similarly, just that it's not quite the same. So we get client, make a loop, while new clients punct empty is not empty. So while there is something, client is equals new clients front punct lock. So front gives us the entry on at the top of the list, while we are inserting at the back. So the clients will be first in, first out served, and on the reference on the weak pointer, the log function transforms the weak pointer into a strong pointer, either a valid one, or if the object already expired, then into a null pointer one. And now basically we repeat this check here, and then we see so this must be empty and this must be null. So if this succeeds, so basically we are coming, we checked, is there a client? Yes, there is a client. Is this null? Yes, it is null. So let's try to make it not null, but then we go back here and we see, is this null? Maybe the client was already handled. And in the ideal case, we would only have one entry, so this we would already bug out. But if this has something, then we check, was our previous iteration capable of actually retrieving a client, or did the client expire in the meantime? And if the client did not expire, then and if the client did expire, then p client would be null, in which case we then try again, and then we will try as many times until we either get a valid client or the list runs empty. And when we are done, we are just returning the client if there is any, or if there is none, then we just don't. Okay. So we are here. We have our clients is equals m get next client. This needs to be I don't like it being there. It makes the code a bit complicated. Right, so we get the thing, and then what we would do is we create first a new socket. Socket is like new. I do not recall how Qt handles this, so we are creating obviously a new socket, but now we have more or less two options. We can socket is well defined, so we need to include the socket here so that we can do something with it. Right. I'm not sure if the server is automatically setting itself as parent, but I think it is. So we'll do the same thing. And if we want to change the parent, we can do that at any later point. We will of course need to mark this thing that it is a server socket, and this is it. So socket header protected void set server socket and friend class port server, because we don't want this to be reachable from the outside. Is complaining, it should not be complaining. Somehow the intelligence is a bit broken here. Right, socket, just put it directly here. And m is, m is server socket true. And here on this end, set server socket. We will not be setting ourselves on this thing, but what we need is the opposite way. So we will need to keep this object referenced on our client, so that if a request from the client comes in, we can then grab data from the socket or push data to that socket. So right here, this goes here, this goes there. So our client will have here a PQ socket, or just let's call it socket. This is null. ptr. I'm just thinking, because if we now delete this thing, the server will crash. So we basically need to make this either into a weak point, or we can use a q pointer, which automatically gets nulled when the object it points to gets out of scope. And I think it's auto initializing with 0 anyways. But there is still a problem. This thing, if we are doing something in the server in a different thread and this thing gets deleted, then it also will cause a crash. So we should how do we solve that? Well, we could just say that you should not delete the thing, but you don't necessarily have the control when you are deleting it. We could make a pointer, a smart pointer that we then, a weak pointer that we then make into a strong pointer, but this breaks the parent semantics, if I recall correctly. The thing then, when the pointer goes out of scope, will be deleted. We don't want to hold on to this thing forever. So if we here only have a weak pointer, then the thing will, well, I said live forever. Sorry, if we only have a weak pointer, the thing will be disposed once we are stop using it, even though it has a parent that might be used. And if we do the other thing and make here a strong pointer, that thing will live forever, even after the parent goes away. That sounds like the less bad of the two scenarios, because we could in principle set some flag when the thing is closed and then try to kill it from this end. I think this is the safer option. Let's go with that. Q shared pointer. Yeah, it should be the safer option. Right, so we have here our client, and on client we set our pair socket to be this thing. Right, so then we set this, and we can make this somehow more elegant. Yeah, we can make this a bit more elegant. Then we can here just, well, it does not really change much. Punkt get our data, so we get the raw pointer, and yeah, we just keep the socket around and clean it up from the other side if needed. Still not great, because if then our server goes out of scope and something keeps a hold on to the socket, then that memory will become invalid. So not great, but usually if you have a server, then the server is the last thing to go. So I think this is an acceptable risk. I think for later, if we can make this somehow more elegant, to ensure that we don't run into troubles. And another thing I have noticed is that since this here runs in a different thread than our buffers here, those two will need to be thread safe. So whenever we want to access them, we need to set a lock. So q mutex mutex let's socket. So here q lock lock reference to send buffer anywhere else, but we use the receive buffer here. Yeah, this is very fast, so we just keep on to the log, although more elegant to oops, to unlock the thing. Okay, should be good enough. Okay, so we are on the server side, then we return here an object. Let's run and see how far we go. Okay, so create server, create thingy. Okay, so we are here, then we put a breakpoint here. Then we are here in our request. This we don't care for now. Port request we ignore, and then here, as you see, this runs kind of asynchronously, since our processing threads, our processing functions are in separate threads, while the main thread is handling this events and messages here. So we see here that this comes from the main function. Okay, so this looks probably correct. So we skip this. This we also don't care for. Then we get here to our breakpoint. So we have our object. We add socket to sockets. But we will be calling a delete later on this thing, I think. On disconnect. Wait, does our sockets have a smart pointer? There's a smart pointer. Let's quickly investigate how this, if this will actually work even remotely reasonably, or if it will not. So the problem might be, it depends how the smart pointers are implemented. If they are using an object property of QObject for their operation, then this could work fine. But if they are using like an additional helper object, then the helper object we created in the other part of the code, since we only return a normal pointer, not a smart pointer, will not be aware. So the new smart pointer will not be aware of the other already existing helper object, and that might be really not good. But here we already run into the assignment operator. Why? Okay, but there is another way how we can probably quickly test this. So we, instead of like stepping through the whole functions, we just go to our thingy, and we see that what it refers is like strong references to, which suggests that the whole thing is where is it? Shared pointer. No, that's a data socket. Wait. No, we sorry, I was mistaken. We only use a normal pointer for the socket. We only use a shared pointer for the data which we track here, so this will not conflict. But somewhere we should have a well, something to get rid of the other object, and we somehow don't. We just take this from here, we return client disconnected. Then more or less by this logic we have a bug here that or rather with the other code, that we never dispose of the client object. And that is not great. For here it's fine, because here we will process the disconnect, clean up our own states, and the server will clean up its own state, so it will work out fine. But in the local server implementation here, we are missing a delete later instruction on this thing. So it will not be quite a drop-in replacement unless we find a nice solution to the object tracking issue. The proper solution would be just to have a proxy object which then will be properly handled and will be able to will be opaque to the rest of the mechanisms, and then we can just keep the proxy around, and if the main one goes away, this will still be fine. But for now, we don't want that, so we will just implement it simply, and then we will look into improving that. So this part will work. So we will get our object, and then the next thing which is missing is our port request function. We only have like 20 more minutes, 25 more minutes, so I'm thinking whether we want to start doing those things, or whether we maybe should try to now find a cleaner solution for our problem with the data, of the sockets that we are potentially creating by keeping a reference to the thing which we are giving out. The problem conceptually which we are running into is that, like with sockets or pipes, you have also on the server side an object which represents the current connection. And here, with this ALPC ports, on the server side, we don't. On the server side, we have our pool of threads which are handling our process function. Where was it? Here. And any of those, so on any of those ports, we might get from one of the connected clients a request. This is why the message always contains the client information. So when we again see this find client, we see that this port message contains data like process ID, client ID, etc., etc., so that we can so that we know from where the current request is coming. So this difference in behavior makes it a bit unelegant to map this behavior to the normal behavior of how the classical QLocal socket operates. What we require for this scheme to work is an ability to write into those buffers, and or rather to read and write into those buffers, and the ability to emit signals on the behalf of this Qt-port socket, so that we can trigger a read and stuff like that. So just a proxy object will not be well, we can create a proxy object which is an entire Q object in itself, and then we can connect signals of one object to the signals of the other, and I think this will be ultimately the way to go here. And that object will then also hold on to the buffers. No, we need to read buffer, we need to write buffer. I'm thinking if we can improve this in some way. For example, that we would only instantiate the object if we are working on the behalf of a client of a server, and we could do this. Yes. Okay. So let's do it. I think this we can do in the available time, and it will be quite reasonable to demonstrate a elegant solution instead of a hack as we did here. So Pocket socket helper Q object Q object and this thing will only be available to our server and socket. It will not be available to the other thingies. It needs a constructor and a destructor. We can try to implement it all in just in the header, so that we keep the source code cleaned up. Although the destructor we probably don't need. This remains private. And we said that we always need the receive buffer, so we need the receive buffer on both ends, so to say. And we need the, I mean, for now let's just put everything here. We could make like an object, port socket helper and port socket server helper, which is derived from a port socket helper, and then add the one buffer which we here don't need to this additional object. But given that the size of a qubit array is like just one pointer, that really doesn't matter. So we will not complicate things too much. If you would be of course using STL vector instead of a byte array, then it would be different, because the STL vector I think needs quite a bit more bytes in memory, while in Qt everything is usually implemented as a wrapper object around a internal private object. So and plus it uses copy on write, so it's really very lightweight. Okay, so we have here our helper, which we just will add here. Then wait, and we need of course somehow to reference this thing. And this will be a strong reference, so Q, although we could also make it a weak reference. First, type def Q side pointer, type def Q shared pointer helper, helper ptr Q. Now my nemesis English orthography. Q weak Q. How do you write weak Q? And the intelligence doesn't help. Q. Well, either it's weak pointer or it's weak pointer. Either with an A. Oh, damn it. Weak pointer. Ref. Well, this is wrong. No, now both don't work. Port socket, but this should. Wait, the Y shouldn't be there. Right, and weak. That's also. There is a typo on the pointer as well. Yeah. That was painful enough. Right, so this thing will keep a strong pointer to its helper. Let's call it H. While the other thing will keep a weak pointer to the helper structure. Path. But let's call it just fully helper. Let's call it helper on both. Right. Weak, strong, very good. Then this needs to be instantiated, and this will be not set socket server, but it will be get socket helper for server. Okay, socket. Where was it? Here. So this thing sets this and return should be mp socket helper. mp socket helper. This automatically makes it into a weak one, and this is then automatically set, but we need to create it. in the constructor. Actually, we can, I think, create. This is more elegant. Okay. Then of course we run into the next thing that and buffer, but this is just a small inconvenience. Right, and we have the strong reference, so we can always do whatever we want. And this and here will only have this weak reference. Right here, so here go back to just creating new socket. This not QSHAT, but that was wrong. Zack. Helper is equals socket get socket helper for server. Okay. Then we just return this like this. Yeah. Cute. And now the scheme is that whenever we do something with our helper, we first lock it to get a strong reference, and then we check whether we actually got one. If we don't, then we bug out, and the thing will remain working as long as our client. But then still we are missing one thing: signals. That's why we make this whole thing a queue object. Or we just call it oops. Yeah, protected, and here signals. We could do it differently. We can just keep it as small as possible, so this kind of just make signals last. Okay, what signals do we need? Let's see. QIO device. Ready read. Well, it sounds useful. Bytes written. This is also useful. About to close. This might also be useful. Let's just go with ready read and bytes written. We don't want to complicate things too much. So we add here those two signals. So ready read is triggered, as you might remember from our initial look on the networking example, whenever some data has been received and the application is supposed to read them and then prepare some sort of reply. And bytes written, I don't think we use that, is triggered whenever something was sent over the network as an or over the pipe, as an indication that more things could be put into the buffer if the buffer was said to be limited in size. Yeah, so those two we will want, and now we will here when we created there. We'll just connect. So first is the sender, so helper, comma signal, read with this signal, read. This is quite nice that we can connect a signal to a signal, and if the other signal gets signaled, this needs to be punct data. And if the other signal gets signaled, and if the one signal gets signaled, it signals the other signal. Otherwise, we would need to make like a slot with then just as one task to make a signal emit. So this is quite convenient. Will this work correctly? It will work reasonably well. There might be an issue generally with this, being that if we emit a signal to read, then we don't have a reply ready. So the other end sends something to us and would get an empty reply back, and this would not be something we would want. So we would need to somehow find a fix for this, but this will be something for the next lecture. And since you have your final project assigned, there will not be any homework either today nor during the next two lectures that we still have in the semester. You should focus your programming time on finishing the final project. If you have any questions, you can ask them at any time. Yeah, and during the next lecture we will continue. So now the client side is well, not fully complete. We are still of course missing here reading data, etc. But the next big workplace will be to handle the operations here on the server side. Yeah, and that is it. So we'll see each other next week. Have a nice weekend. Bye bye.